The next speaker is going to talk about analyzing JavaScript using LLMs, and we are going to invite to the stage Noga Moscovich. She's a data science tech lead from IBM Trusteer. So please, Noga.
Hello, everyone. Hi. My name is Noga Moscovich, and I'm from IBM Security. Today, I want to talk to you about a cool project that we did, analyzing JavaScript using LLM. The project was led by Shimon Benosovich and Adrian Finkelstein. Let's see if it's work. Okay. So I'm from a business unit called Trusteer, and in Trusteer Solutions, and this is from IBM's website. We authenticate customers, detect fraud, and protect against malicious users across all channels. And today I want to focus on protect against malicious users. So in part of doing that, we need to detect malicious JavaScript. JavaScript is a powerful tool to create interactive websites, but it can also be used in dangerous ways. An attacker with malicious JavaScript can steal sensitive and personal data such as credit card information, login credentials, browsing history, and more. It can take control of your device and displaying unwanted ads, crypto mining with your processor, or even launching attacks on other devices. It can do code injection and manipulate your web content or redirect you to efficient sites. So it can do a lot of damage. Here are a few examples of JavaScript attacks, just to see how popular it is. JavaScript malware infects Windows PC with threats. JavaScript malware targeted 50,000 users at dozens of banks worldwide. British Airways data theft, eBay false victim, and Fortnite gamers exposed to account hijacks, and there's a lot more. This is just from 3 minutes search on the web. So in our lab, web researchers have various tools to determine if a JavaScript code is malicious or not. But they have thousands of code snippets from multiple sources each month. They need to prioritize what to look on, and many of them very similar to each other. And I want to focus on this similarity. This similarity can do is from various things, such as similar obfuscation tools or different browser versions. If the code is malicious, then attackers tend to change the parameters and domains between the attacks. So all of this gave us many samples of JavaScript with minor changes between them. So how do we help our researchers find the malicious samples? We use LLM, obviously. This is why we're here. So what is LLM? I'm not going to cover that, and I'm assuming that everyone in this audience know what it is at some level. So just for the record, LLM stands for large language model, type of AI trained on massive amount of text data that lets it understand and generate human-like text, exactly like this paragraph were generated by Gemini. When I asked it to describe in 2-3 bullets what is LLM. Okay, moving on. So our goal was to cluster thousands of code snippets in an efficient and fast way. As I said before, we have many samples that are very similar to each other. We wanted to find the outliers, the samples that are malicious, the ones that our researchers will want to investigate and check, just like searching a needle in a haystack. So we did clustering to find these outliers. And the first thing in doing the clustering, we used the embedding layer of the LLM. The embedding layer is the initial step for an LLM to understand text data. Models and computers in general can't understand words and text, as we all know. They only understand numbers. So the embedding layer transforms words into numerical representation and enables the LLM to process and understand the meaning of the words. So words with similar meaning will have similar vector representation. What we did is we converted each snippet into vector using the LLM embedding layer. So you can see here an illustration. We have code snippets of JavaScript go to the embedding layer, and each code snippet become a vector, which is the numerical representations of that sample. After that, we took all these vectors and put them in clustering algorithm. In our case, we used the good old K-means algorithm. We did try several others clustering algorithms, so DB-scan, aggregation clustering, and so more, but K-means gave us the best result, so this is what I'm presenting now. For anyone who doesn't remember or doesn't know, in 2 sentences what K-means is. K-means algorithm groups data points into predefined number of cluster, which is the K in K-means, and then iteratively assign the points to the nearest cluster center, recalculates the centers based on the assigned points, and repeats until the grouping stabilizes. So this is K-means algorithm, and we ran the algorithm several different Ks, and found the right K by plotting cluster quality methods. I will show this shortly in a few slides. So we took all our samples, convert them to vectors, put in a clustering algorithm, and got K clusters. In our case, it was with K-means algorithm. After that, we wanted to find the outliers, as I said before. So the outliers are the sample that doesn't belong to their cluster, meaning they are different from the rest of the samples in their cluster. And this increases the chance that these samples are malicious, or at least suspicious at some level. To calculate the outliers, we set a threshold distance from each center and took all samples with filtered distance. You can see here, illustration in this small part of the presentation. Of course, each clustering algorithm may have different outliers method. Because we used K-means, this is what works best for us in that way. So a quick recap. We have many samples that are very similar to each other. We wanted to find the outliers out of them. So we took all the samples, put them to embedding layers, and convert them to vectors, and then ran clustering algorithm on them. We then got K clusters, and in each cluster, we found the outliers. These are the outliers that we sent to the researchers for investigation. Experiment. So we check our method with several experiments. I'm going to present one of them now. In that experiment, we used one data source. We have multiple data sources in our lab, but we did an experiment, so only one of them. For the train, we took data of 2 months, which was about 64,000 samples. And for the test, we took one following month, which was about 16,000 different samples. You can see here a word cloud, a real word cloud for one of the clusters in our data. So our data was just many samples of JavaScripts, and this is a popular coding name from JavaScript. So all our data, the test and the train, are the code snippets to embedding layer and became vectors. We then fitted with the train the clustering algorithm, and then did predict on with the clustering algorithm on the test samples. So the clustering algorithm was created with the train data, as we usually do in machine learning, and then we did predict on the 16,000 samples, and this was our results. So in our case, we got K equals 9. You can see here the graphs. I know it's small. I don't have much time to go over that anyway, so just in 2 sentences. The left graph, if you see there, it's the elbow method with within cluster sum of squares that checks out how much the data points spread out inside the cluster. And the silhouette square for the right graph is another method that all this time. Okay. So. Okay. I don't hear any difference. Okay. So the silhouette score, I hope you hear me okay. The silhouette score in the right graph is another method to check cluster quality. And here are the cluster size distribution. You see that the biggest cluster contained 44% of those samples. And in total, we found 139 outliers, which is 0.8% of the 16,000 samples that we have. 95% of the outliers were labeled correctly, meaning they were actually outliers. They didn't belong to the cluster. They were different. And 80% of the outliers were malicious at some level. Not every malicious JavaScript have the same severity. And we found one fraudulent attack. We didn't expect that. It was a nice bonus that this attack may otherwise could have been missed. So the method advantages. It's a simple solution, relatively. It's low cost because the LLM is open source. You don't need to invest resources in order to train and create the embedding model, and you also don't need to invest resources in order to update the embedding model with the new data. All we need to do is retrain the clustering model, and when the researchers see there is a gap in the results, they can decide to retrain the clustering model with the latest data as they need, and that's the whole method. In the future, we want to expand this project to include ranking. So not all outliers are malicious, and even the malicious samples have different severity, as I said before. And there can still have dozens of outliers. In the experiment that I showed you, it's from one data source. In our lab, we have multiple data sources, so our numbers are much, much higher, and the researchers need a way to prioritize their work, and we want to do ranking to help them with that. So what we plan to do is to do a supervised learning, to take a classification model. The input will be a code embedding, just like before, the vectors, like we did with the LLM. The labels will be the researchers' feedback, because all the time they see samples and they label it. It's malicious, it's not malicious. We can also add suspicious labels. We can do whatever we want. The outputs will be the model probabilities, and the ranking will be according to these probabilities. And that way we can help them to prioritize their work. That's it. Questions? Thank you. Do we have time? Yes. The embedding model, we didn't do fine-tuning. We took a model that was trained on code. That's it. Thank you very much.